So hello, everyone. Thank you for coming. The title of my work is Design, Design, Development, and Deployment of Real-Time Drum Accompaniment Systems. This work was supervised by Dr. Sergi Jorda and started back in December of 2019. Oh, sorry, can't find my mouse. Okay. I'll start with a brief overview of the thesis, then we'll dive into some of the technical aspects of the work. The main motivation behind my work was to explore potentials of generative machine learning for developing interactive tools, specifically tools that require constant and intentional interactions. One decision we made from early on was that we didn't want to solely focus on architectural advancements. Rather, we wanted to focus as much on deployment, meaning that studying how can we enhance the model's application through deployment rather than just approaching the enhancement from an architectural perspective. With all of these in mind, the very first decision we made was that we wanted to focus on real-time generation, and the reasoning behind this decision was that real-time generation is more likely to require constant and on-the-spot interactions from users. The question then was on what aspect of real-time generation should we focus on. At the time, I was very much interested in sequencers and drum machines. I remember for the SMC Masters course we had with Sergi, I made a PD emulation of the IntelliGel Metropolis sequencer, and then we had to perform with it as a course requirement. What became very clear to me as through that experience was that a sequencer is more than a tool that simply does automation. In fact, it's an instrument. In the context of the PhD, I wanted to explore this concept further. To be more specific, the initial idea I came up with was to explore how to utilize generative neural networks to come up with new ways of interacting with sequencers. At the time, most sequencers employing some form of a data-oriented generative process were focused on controlling a drum or rhythm sequencer using some high-level control parameters, specifically utilizing a 2D space populated by drum patterns. The idea then was that perhaps we can focus to further this concept from another perspective. That is, instead of explicitly controlling the pattern generation process using some high-level controls, we focus on developing a sequencer that autonomously decides on what patterns should be generated directly based on users' musical performance. That is, the decision was then to focus on developing sequencers that act as autonomous rhythm accompaniment sources. With this decision in mind, the next question was to figure out what aspect of user's performance should be provided to the sequencer so that it would be able to come up with the accompaniments. The idea was that instead of trying to focus on utilizing every aspect of the user's performance, we will focus only on rhythmic aspects of the user's performance. This decision was in fact inspired by a series of drum generation models called Groove that was released just about the time I started my PhD. To explain briefly, Groove is a collection of generative models that try to achieve a number of different drum generation tasks. One of these tasks, called TapTamDrum, was focused on developing a generative model that would convert a single voice rhythmic loop into a multi-voice drum pattern. This was the starting inspiration behind most of the works we've done in the past few years. Specifically, while TapTamDrum wasn't focused on real-time use, we wanted to explore how to leverage the ideas proposed in TapTamDrum to develop real-time drum accompaniment systems. This inspiration led to the development of the first accompaniment system we made, which was simply a sequencer that would be controlled using a real-time rhythm received from a performer. After some evaluations, we identified some crucial shortcomings in the first system and focused on developing the next iteration with the collaboration of a musician. Lastly, we developed the final system, which moved away from this idea of a loop-based sequencer and focused more on direct, long-term sequential accompaniment generation. The main approach in the development of the thesis was that instead of focusing immediately on developing the most comprehensive system, let's start with a very small one and incrementally increase the scope based on the findings at each stage. This approach enabled us to explore a number of secondary topics that heavily shaped the trajectory of the research. To name a few, we explored how our symbolic-to-symbolic approaches can be extended to audio. We also explored how research tools in this domain can efficiently be deployed so that they are accessible to a wide range of users outside of the research community. And lastly, we also worked on deployment beyond software environments to allow users to better experiment with the context in which our models were to be used. For the remainder of the presentation, I'll first focus on the first three systems, then we'll have an overall look at the developments, and then finally wrap up the presentation. Before we dive into the technicalities of the thesis, a quick note on the structure of the following three sections. The following sections are structured in the same order in which the development of each system took place. That is, for each work, we started with formulating the real-time environment and identifying what the role of the generative model is in the decided environment. Then we focused on developing the architecture, and once trained, we validated that the models were successful in learning the underlying objectives. Once we validated the models, we then deployed them. We designed the full system around the model. And lastly, we conducted user evaluations so as to identify what needs to be improved in the next iteration of the work. With that, let's dive into the main discussions, starting with system one. When we wanted to figure out the scope of the first system, we had to consider that there were many topics to be explored. As such, the idea was that let's simplify the task so that we can explore as many aspects as possible under a constrained environment. The idea was that hopefully this will lead to some foundation on which we can develop more complex systems. With that, the decision was then to develop a loop-based sequencer that would be controlled via a user-performed rhythmic pattern received in real time. In other words, the idea was to develop a model that would convert a single voice rhythm into a multi-voice drum sequence. Note that in both cases, that is, that both the input and output, we wanted the generated sequences to have velocity and timing dynamics. Then the question was, how can we come up with the training data? Specifically, how can we come up with single voice rhythms that are correlated with the drum patterns? For this, we used the ideas proposed in Groove's TapTamDrum, where the authors proposed that the single voice rhythm can simply be extracted by flattening the polyphonic sequence. That is, we simply go through the polyphonic sequence one step at a time and grab the loudest event in that time step and move it into our single voice representation. From now on, every now and then, I might refer to this single voice representation as a monotonic groove, or groove for short. The next question was that if the rhythms come from drum patterns, how can we use this in an accompaniment setting? The idea was that once the system was trained, we would in fact extract the groove from a user's performance in a similar manner, meaning that the polyphonic sequence that would be coming, the MIDI sequence that would be coming into the sequence, we would just flatten it and use that as the input to the system. To develop the generative model, we focused on generation of two-bar loops using a fixed grid resolution of 16th note. Then we used the Groove MIDI dataset, which contains over 13 hours of drum improvisations on an electronic drum kit. Moreover, we only focused on the 4/4 subset of the dataset, as majority of the data was in this meter. Subsequently, we used the representations proposed in Groove to represent our sequences. The representations are essentially piano rolls, meaning that different features of the sequences are annotated using grid relative representations, using a set of binary values to denote the onsets, a set of continuous values to denote the intensity or velocity level at the location of onsets, and also continuous values of offsets, or also called microtiming, denoting how far off from a fully quantized grid line the events are located. For the architecture, we decided to use transformers. This may sound a bit counterintuitive, as transformers are generally used for large sequences. The reasoning behind this choice was that eventually we wanted to move beyond loop generation and work with much longer contexts. So this was a good opportunity to validate the architecture, the training process that was involved, and also the data representations that we were going to use before moving on to future experiments. For training, we would simply grab samples from Groove MIDI dataset, then flatten them. The model was then trained to convert the flat sequence back into the original drum sample. And during training, the comparison with ground truth was done by jointly comparing the generated features with the targets, namely comparing hits, velocities, offsets using different loss criteria. We then trained many different configurations of the model. 4 were selected for validation. Validation here refers to ensuring that the generated content are statistically correlated with the training data. As I mentioned before, the main objective of the validation at this point is to ensure that the model was successfully trained for the task that it had to do, which in this case was being able to actually convert a groove into a polyphonic multi-voice drum pattern. The validation of the selected models was done from different perspectives and established that our models were on par with Groove's tap-to-drum. We also identified some shortcomings in the generations to be improved in future iterations. I won't be discussing the technical details of the validation process. I've discussed them in section 3.5 of the manuscript, and I'll be more than happy to talk about them during the Q&A session. Once we validated models, we then deployed them in our real-time environment. The prototype we developed consisted of a pure data front end, which handled processing and playback of generations, and also provided some controls so that the user could interact with the model's parameters. Moreover, the generation happened in a Python backend communicating with the interface through an OSC connection. A key challenge we had in designing the prototype was the limited temporal context of the models, which was fixed to a 2-bar window. This raised a critical question: how could a model with such restricted context effectively handle longer sessions? Rather than tackling this limitation architecturally, which means that dealing with increasing the scope of the model, we tried to approach it from a deployment perspective. To address this, we decided that user performances would occur within a looping context, and leveraging this analogy, we incorporated a concept that is commonly used in loopers called overdubbing. By implementing overdubbing, we allowed the model to access events from the full performance rather than just the latest 2-bar segment that was available. Once the prototype was prepared, we began interacting with the system to gather insights prior to conducting user studies. Several key observations emerged during these early tests. The overdubbing mechanism significantly improved the system's coherence in the beginning of the session. However, this came with a trade-off. As the buffer became increasingly filled, the range of variations in the generated outputs diminished. This meant that performers needed to develop strategies to manage this limitation effectively during longer sessions. Moreover, the system demonstrated a high level of sensitivity to both velocity and timing dynamics. As such, unintended accidental events performed by the user and the type of MIDI device that was used would noticeably impact the generations. At this point, we began collaborating with Raul Refri, a renowned professional musician, composer, and producer from Barcelona, who kindly agreed to assist in evaluating the system in an improvisational context. To prepare for the sessions, we introduced him to the system, offered a thorough explanation of its conceptual framework and the controls that were available for interacting with the system. We then invited him to engage with the system through improvisation. Let's watch a short recording of the session. During his initial interaction with the system, Raul expressed feeling somewhat overwhelmed. This reaction stemmed primarily from the extensive range of controls that were available, which made it challenging to adapt quickly in a real-time improvisation setting. He noted that the system, as it was more suitable for a production-oriented context. However, it might not be as well suited for a spontaneous real-time improvisation, in which meticulously adjusting the generations was not feasible. For real-time use, he emphasized a preference for a much simpler interface with minimal controls and a greater degree of autonomous system behavior. Before moving on to designing the next iteration of the system using Raul's feedback, I should briefly talk about our deployment strategy. One objective we had from the beginning was to develop tools that would be accessible to the general public. However, accessing the prototype outside of the lab proved quite challenging due to its technical setup requirements. This pointed to the need for a more efficient, user-friendly implementation, such as redeveloping it as a self-contained VST plugin to simplify installation and enhance accessibility. To address this issue, we re-implemented the prototype as a VST plugin using Juice and LibTorch. Here is a view of the redeployed prototype, and let's just see look at a quick video if the audio is better. The redeployment process, while it was essential for improving usability, proved to be extremely time-consuming. It came at the expense of focusing on our primary research goals. This highlighted a critical realization that manually deploying every system in such a detailed manner is not sustainable. Then to address this, we needed a way to automate the more technical and repetitive aspects of the deployment process, freeing up time and resources for focusing on the core research. As such, we developed a wrapper called NeuralMidiFx, which would automate many aspects of the deployment process to the extent that the primary focus of the researchers would be on the model-related aspects of the deployment process. Despite the limitations of the initial system, it served as a foundation for future explorations, contributing both architecturally and in terms of deployment. Architecturally, it led to the development of an efficient transformer-based groove-to-drop model and validated our chosen representations. On the deployment side, we explored ways to enhance the application of a constrained model. Also, the deployment process resulted into the creation of NeuralMidiFx, which heavily reduced the cost of our future developments. Additionally, evaluating the system revealed critical challenges and shortcomings that must have been addressed in the next iteration of the work. With these findings, let's move on to the second system. For the second attempt, we wanted to develop a system that was more suitable for a live performance setting, meaning that we wanted it to be more autonomous to the extent that it would require less active intervention from the performer. Moreover, we wanted to focus on providing meaningful controls that allow for quick and effective interaction with the system. Most importantly, unlike last time where we developed the system and just presented it to Raul and asked him to evaluate it, this time Raul kindly agreed to be involved from the outset, so this work was done in close collaboration with him. The main idea for the second system was to develop a system that was a hybrid between a sequencer and an accompaniment generator. That is, instead of just expanding a groove into a multi-voice drum pattern, it could be able to rhythmically adjust some pre-selected patterns based on the rhythm performed by the user. The idea was then to allow for user-controlled or rule-based automation of the interpolation between the user-agnostic sequencer mode and the full-on accompaniment mode. For the second system, we decided to start with developing a variational model. This would allow us to interpolate between users' rhythm and pre-selected patterns encodings. Then we had this idea that perhaps instead of starting with one pre-selected pattern, we can have more selections. With this choice, given that each pattern would be associated with a latent encoding, we could allow the user to not only change how much their performance should impact the response of the system, but also how close the generation should be to a number of preset patterns. This way, when the user didn't want the system to respond to their performance, they still could utilize the system as a sequencer, controlled by navigating the latent trajectories between the pre-selected patterns. Let's discuss this idea in a bit more detail. For the final setup, we decided to use two predefined patterns. Then this would allow us to then with this, we could allow for continuous interpolation between the two patterns, resulting in many more intermediary patterns, each correlated with the select preset ones. Then we would introduce a third encoding, which was fully correlated with the user's performance. Subsequently, we would be able to play back a drum loop that was an interpolation of all 3 points. In this setup, we end up with this triangular subspace of the latent space with a few attributes. Along the bottom side of the triangle, the system simply interpolates between A and B while ignoring the performance of the user. Then, along the other two sides, the system will interpolate between the user performance and only one of the pre-selections, ignoring the other pre-selected pattern. In general, closer to the top of the triangle, the system essentially only takes into account the user's performance. That is, it tries to simply follow the user. On the other hand, going towards the bottom, the impact of the user performance diminishes, where at the lowest trajectory, system fully ignores the user, hence somewhat leads the session. This trade-off between following and leading can quickly be specified by the user, or even more importantly, can be automated using some predefined rules. The idea for us was that with these rules, perhaps we may be able to introduce some level of autonomy to the system. That is, we can allow the system to automatically decide on the function of the drums at any point during the performance. The architecture developed was a variational version of the previous system. One note is that we also modified the architecture slightly to improve the shortcomings of the previous model. The shortcomings were mainly in terms of lower dynamics of the generations, which we managed to improve them quite drastically with the new setup. As opposed to the last system, this time we actually wanted to think more about the control mechanisms that we wanted to incorporate. Throughout the development of the work, we decided that we wanted to incorporate the controls such that the performer could quickly change or alter the generated patterns. Also, along the same lines, the decision was to control the generations globally instead of allowing for very detailed and meticulous manipulation of each of the patterns that were located in the corners of the rhythm space that we had. To this end, the control mechanisms were introduced after a given pattern's encoding prior to the decoding process. The first set I decided on was based on the style tags available in the GrooveMidi dataset. The idea was that style can be useful to quickly change the velocity and timing dynamics, as well as the voicing used and the score used in the generations. The second set was incorporated based on our observations of how Raul interacted with the system during our initial evaluation sessions. In these sessions, we allowed for we had a number of sliders for every single voice in the generations, and Raul could control the density of each of those voices. what we realized was that in most cases, the sliders were used to simply fully remove a given voice. Then the idea was that if that's the use case for it, we would just allow for simply muting or rather removing a voice from the generations. Then we came up with this idea that in fact maybe it would be interesting if we can have a feature that would allow for not only removing a voice from the generations, but also re-rendering the remaining voices, hoping that it would result in a new pattern that felt somewhat correlated to the original pattern prior to muting that specific voice. We then validated the models from different perspectives to ensure that the model was capable of accomplishing the tasks required in the deployment process. This validation was done from different perspectives to ensure whether the model can reliably achieve the objectives at hand. That is, whether it is able to convert a groove into a drum pattern, whether it's able to modify the generations based on the control parameters, and also whether it can interpolate between different patterns. Once we validated that these objectives were achieved, we moved on to deploying the models in the real-time system. This time, the deployment was done directly using NeuralMidiFx, resulting in the plugin shown here. For the input management, again, we had this looper idea, but this time we modified the overdubbing process slightly. Instead of indefinitely overdubbing information, we used the rule-based approach to keep a registered event in the buffer only for a specific period of time. This would allow us for controlling how much of the performance context would be used to actually base the generations on. Also, while the user can manually control the playback position in the triangular drum performance space, we implemented some rule-based approaches to automate the navigation so that the user wouldn't need to manually navigate the space. Essentially, somewhat tried to simulate an autonomous behavior. Here is the demo of the system. In this demo, I have basically two patterns selected to an A and B sides, and then we start jamming along with them. And as more information gets encoded in the input buffer that we have, they would impact the overall feel of the rhythm more and more. One thing I should mention is that the A and B patterns, they can be achieved by randomization, so you can randomize patterns and lock them to those points, or during a performance, wherever you are within this space, you can actually snap it to one of these corners. So it's not that necessarily these are selected prior to a given session and you use them as presets. There is, in fact, like when you snap it to a corner, it's as if you're zooming into a subset of that space that you are interacting interacting with in that specific moment. Back in February of this year, Raul also did a performance with the system at CCCB in Barcelona. Let's watch a short snippet of that. The new system was certainly more usable in a live performance setting to the extent that Raul was comfortable with performing with it in a live environment. That said, given that it was still a hybrid between a sequencer and an accompaniment generator, the system still did require intervention at times. The rule-based approaches did reduce the amount of direct manual interaction with the system, but it was certainly not enough to fully remove this dependence. In terms of control, the mutes were very effective to control quickly modify the generations, while the style controls were less appreciated. As I said earlier, the idea with utilizing the styles was to control the general feel of the generations quickly during a live session. That said, perhaps there was a bit of short sight in actually using the style controls. As you can see here, I'm using in the UMAP projections of the latent encodings corresponding to the test set that we have. We can see that there is a clear cluster of patterns heavily populated by different styles. This is not surprising given that there is a lot of crossover between different styles, which essentially means that such metadata shouldn't be treated so literally as we've done it in our second system. Another note here is that even if these tags were fully descriptive of the patterns, the incorporation of these controls essentially meant that interpolation of patterns would also be done within a specific style, hence quite limiting a big subset of trajectories that could have been explored and now that would most likely wouldn't be possible. In fact, a duo from Barcelona called Desert also used the system in a production setting, and one of their comments was that for them, such a tool should be used for exploration of new rhythms rather than imitating a given style. And simply having the style controls kind of biases the use case towards imitation as opposed to exploration. The last observation we had was that the model generally tends to generate overly active patterns with lots of varying velocity dynamics. As such, whether these dynamics are or are not utilized in the synthesis process heavily impacts the perception of the generations. This is, in fact, an aspect we had not explored much up to this point. To further explore the impact of synthesis, we wanted to see whether we can redeploy the system in a manner that would actively require the user to decide on how to interpret every aspect of the generated features. To this end, we decided to develop a hardware Eurorack version of the Groove Transformer. I think I forgot to mention that the second system is called Groove Transformer, but the decision to focus on Eurorack was that there was, in Eurorack environment, there is no plug and play behavior. In such environment, the user needs to actively and quite intentionally explore how every aspect of the system should be routed and interpreted. With my colleague Nick Evans, we managed to make the Eurorack implementation of the Groove Transformer. And given that our models were computationally very lightweight, we were able to run the generations on a consumer level single board computer running Linux. We also utilized a secondary board called Daisy Seed board to handle the input-output, MIDI, and control voltages. Let's see a short demo. In this demo that I'm going to show in a second, the first part, we're just using the module as simply as a sequencer where you're only using it to interpolate between a number of pre-selected drum patterns that you have. And in the second case, we are actually feeding a groove to it, but that groove, in fact, is coming from a sequencer rather than being performed on a MIDI keyboard. To wrap up, the second system was certainly a more successful attempt than the previous one. That said, many improvements in terms of system autonomy should have been made, which we try to explore during the development of the third iteration of the work. And with that, let's move on to the last module that we developed. In the third attempt, the main focus was to develop a more autonomous system that will require minimal intervention from the user. We believe that prior explorations showed some inherent limitations to the loop-based approach, and as such, for this attempt, we focused on developing a model that would rely less on rule-based approaches and instead would autonomously decide on the generations, utilizing the full performance context as it unfolded over time. In this case, to properly model the performance, we believe that relying solely on drum patterns wouldn't be enough, and as such, we focused on utilizing multi-instrumental data that would allow the model to have some understanding of how given incoming rhythms should be interlocked with drums. Knowing that we needed to model a much longer context, the computational cost also would be much higher than before. Hence, we needed to explore ways of ensuring that the final generative model would comply with our real-time requirements. The initial idea we had was that we would utilize a sequence-to-sequence model in which the groove would be encoded on the one side and the drums would be decoded autoregressively on the other side. That said, when thinking about how such model would be used in real time, we identified a major issue. The issue was that with this setup, the generation of any upcoming drum event relies on the entirety of the user's performance up to the time of generation. That means that this model could only be used to generate a single time step of drum events in real time. The major implication here is that when we start predicting the next event to be played at the beginning of each step, the model takes some time, of course, to come up with that generation. As a result, there are situations where the timing of the generated event corresponds to the period during which the generation was actually happening. In such cases, the generated event, of course, won't be playable. One solution is that we can delay every generation by a specific amount, ensuring that by the time that the content is created, it would be playable. However, in our case, this would be quite problematic because the representations we used are grid relative, and the representations that we have rely on offsets, which are calculated from a reference grid corresponding to the internal clock of the system. As a result, delaying the generations wouldn't be an option for us because the metrical grid perceived by the performer would be out of phase with the internal clock of the system. As such, we tried to think how can we avoid this issue by perhaps better formulating the task. The idea was that we need to develop a model that would not only rely on the user's rhythmic performance up to a point, but also be able to, but also rely on a prediction of where their performance will be heading. If we manage to do this, that at any given time that the generation was to occur, we would be able to generate sequences longer than a single time step. In this case, by managing the generation rate and the length of each generated segment, would be able to generate sequences that were partially overlapping with the next generation, with the next time that the generation was actually taking place. This way, this would mean that at any time that the generation was taking place, we already have some previously generated events ready for playback. With this idea of sort of anticipating the user's performance, we started rethinking the architecture. With that, we decided to use a single causal transformer, which would model the sequential ordering of the user groove events simultaneously stacked with the drum events. The benefit of this model was that it would allow for generating arbitrarily long sequences, partially relying on the prediction of users' performance. For example, in the figure I'm showing here, in the middle one, when we start generating a segment at the end of the fourth time step, we have to predict what user's performance will be at the fifth, sixth, and seventh time step in order to be able to generate the upcoming drum events. Note that when we generate the next segment, starting at the end of the eighth time step, We dismiss the previous predictions of the user's performance, and we only rely on what was actually performed by what was actually performed during the playback of the previous segment. So the representations we used here were similar to the previous architectures, with the distinction that groove and drum hits, velocities and offsets were stacked together. Note that while the velocity values are predicted on the output side, we don't feed them back into the input. This decision was made given the previous system's heavy reliance on the dynamics of the incoming rhythm. To have a more controlled environment for our experiments, we fully dismissed the velocity information and focused on only utilizing the hit and microtiming information for predicting the generations. As I mentioned earlier, we wanted to also model the interlocking of the instrumental pairs. Hence, we used a select subset of LAC-MIDI dataset that contained either bass, guitar, synth, or lead parts paired with drum patterns. To further control our experiments, we limited the maximum temporal context of the model to 32 bars in 4/4 meter using a 16th note resolution. We then validated the model from different perspectives to ensure that the generations were correlated with the training data set. A few observations was that the model generated less active patterns relative to the test set. That said, this lower activity seems to be more in terms of voicing than the rhythm. Also, the generations were internally as diverse as the test set. When primed, in fact, when primed with the same starting point as the test examples, the generated scores would also be more correlated with the test sequences. I should note that much more extensive validation is required to better understand the behavior of the model. That said, despite the identified shortcomings that should be improved in future iterations, we continue to focus on developing a real-time application around this model. As I mentioned earlier, the idea was that in the real-time plugin, we would schedule the generations at desired specific periods and then utilize users' performance and potentially the prediction of their performance to generate a segment of drums. For the real-time application, however, we identified a number of additional features that could be incorporated into the real-time environment. The first feature was that by selecting the rate at which the generation happens, the system's reliance on the prediction of users' performance would vary. As a segment gets longer, the reliance on the prediction becomes more, essentially resulting in lower or rather slower responsiveness to users' immediate performance. This can in fact be a useful control parameter with which the user specifies how responsive they want the system to be to their performance. Moreover, we realized that given that the model predicts the trajectory of users' performance, we may be able to generate long drum patterns without relying on the user's performance after a certain point, essentially allowing the model to self-improvise on its own, fully agnostic to what the user is performing. Also, in fact, we can utilize both users' predictions and the actual user performance by mixing the two groove streams together. Of course, we can allow the user to specify the starting point of a session, meaning that they can prime the generations with a specific drum pattern that they like. And lastly, while there are no controls implemented, we can allow for users to modify certain aspects of the generations using post-processing of the generated content before being auto-regressively fed back into the model, hence somehow controlling some aspects of the score. With these features in mind, we then deployed the model using NeuralMidiFx. Here's a snapshot of the developed plugin, and let's watch a short demo of it. one note to make is that given the 32 bar maximum context of the model for sessions that go beyond this limit, we essentially shift the performance by 8 bars. This might result in less reference to be made to earlier parts of the performance. In future iterations, a more context-aware model can perhaps be better suitable for such use case. We haven't done a formal evaluation yet. However, through our interactions with the system, we've identified a number of main challenges to be addressed prior to conducting user evaluations. Firstly, the trajectory of a jam session with the system can quite change depending on the starting point of the predictions. For now, we rely on a single bar of rhythmic information from the user to decide what the starting drum pattern should be. This can be quite useful because every time you redo the session, you might end up getting quite different results. However, maybe a single bar of rhythm to base the starting point of the generations on is not enough. So that needs to be addressed, definitely. Another observation was that the system has a tendency to generate quite repetitive patterns. This is expected, given that the data we used was not recordings of improvisations, but rather songs that are specifically in rock, and in fact, most of them were rock and pop songs, which mostly adhere to a very typical structure, like an intro, verse, chorus structure. So the idea, this kind of leaves an interesting question, which is, how can we leverage this type of data to generate more dynamically varying accompaniments? We speculate that perhaps one approach for doing so is to leverage the structural information available in our training data. For instance, we can bias our training process towards training samples that are more structurally diverse. Alternatively, perhaps we can even condition our generations on these information. Which in essence, if we are able to do that, perhaps we can allow the users to kind of specify certain trajectories, structural trajectories of the performance. The system presented here is still an ongoing work. We are still working on it. Despite the improvements to be made in the coming year, we managed to develop a long-term accompaniment generation system that is certainly more autonomous than the previous one, meaning that it requires less active intervention from the user. Moreover, with the idea of generating overlapping segments, we managed to allow for undelayed and uninterrupted playback of generations while being fully synchronized with the internal clock of the system. This was the last accompaniment module developed in the context of my PhD. With that, we can move on to the final parts of the presentation, discussing and reviewing the 3 developed systems. The very first discussion I want to bring up is on this idea of simply relying on a monotonic groove to model users' performance. Of course, this can sound like a very reductive process, but for us, it was in fact a very deliberate choice, a choice that brought us a number of affordances. The very first affordance was that given that the system, the modules are reliant only on rhythmic events, it can very easily be adapted to work with audio inputs. This can be done simply by using an onset detector that can operate in real time. If the user performance was modeled more comprehensively in terms of pitch, timbre, duration, then this adaptation wouldn't certainly be possible without some very costly intermediary processes. In fact, we've managed to port the pre-trained DDC models shared by Chris Donahue into our plugin environments, and the plugins can now work with audio inputs. Let's watch, maybe I'll actually skip the demo. Sure, maybe, yeah. The second affordance was that training only on rhythmic information makes the system less specific for a specific use case. This wouldn't be the case if you focused on accompaniment generation for a specific instrumental setting. For example, if you focused on generating drums for guitar performances in a very specific style, then the system would be more suitable for a very narrow subset of applications. The idea here was that by not having a specialized system, we would perhaps be able to encourage users to experiment with the context in which the generative plugins are used. That said, of course, when it comes to the output of our modules, they still generate drum patterns, which certainly can bias the users towards a specific way of interpreting the generations. Regardless, this idea of groove leaves a lot of room for experimentation with the context in which the systems are used. In fact, in our latest collaboration with Raul, we used the groove transformer for an organ show, a context which was absolutely not envisioned during the development of the work. I don't have proper recordings, video recordings of the show, but there are some short audio snippets. In this performance, what was happening was that Raul was performing on the main organ while the system was driving two smaller MIDI-enabled organs. For this show, my colleague Nick Evans developed a Max for Life patch, which would basically train a Markov model on Raul's performance in real time. And the groove transformer model was sort of used to rhythmically cue the Markov model for the generations. Despite the affordances, of course, there are a number of limitations. We've done some explorations to address some of these limitations. The very first thing is that in terms of the methodology that we used for training the very first two systems, the models that we trained were those first two models were trained on a flattened version of drums. Without any sort of post-training deployment strategies such as overdubbing that we used, the models basically learned to only expand the groove vertically into a multi-voice drum pattern. That is, they only reinforce user rhythm without ever complementing it. This is a very limited, narrow rhythmic interaction. To address this limitation, we've done some explorations into alternative ways of reducing a given multi-voice drum pattern that would not result in an equally active representation. These explorations were done in the context of a TapTamDrum dataset in which a number of drummers were asked to represent the underlying rhythm of a drum pattern using only their hands. The hope is that this dataset can potentially be used for coming up with a computational model that would allow for a better reduced drum rhythm extraction process which then can be used for retraining those models. The second major limitation is that although the systems can be used in a diverse set of settings, they are still trained on expert level data. Hence, systems performance may vary considerably depending on the sort of the expertise level of the user. To further explore this limitation, we've collected a sizable data set of hand percussion improvisations paired with drum patterns using over 3,000 participants. This data set called El Bongosero contains a diverse set of users, each with varying levels of expertise. The hope was that perhaps the diversity of the data set would enable us to develop accompaniment systems that were more aware of varying levels of rhythmic expertise. And Of course, and the last thing I need to mention is that the generations are very clearly specific to a multi-voice drum kit. In future iterations, active effort should be paid on encouraging users to actively experiment with the system in different contexts. Of course, as was the case with the URAC module, we developed deployment environments where plug-and-play systems are rare, will naturally be able to force users to actively explore how the generations should be used. Alternatively, the system can be trained to generate more abstract rhythmic streams which don't have these very specific vocabularies associated with them, similar to a drum kit where you generate a kick stream, a snare stream, and so on. In that case, there is no plug-and-play behavior. You have to actively think about how these generated streams should be interpreted. So just to wrap up, my studies resulted in 6 publications, 2 datasets, and a number of open source hardware and software plugins. Last year, we did also a workshop on NeuralMidiFx at AIMC 2023 conference. We've showcased the Groove Transformer URAC module at Sonar Plasty Festival in 2023. Also earlier this year, we used the Groove Transformer models in an installation we prepared for a 6-month exhibition at CCCB. And lastly, with Raul, Nick, and Sergi, we've managed to use our systems in 3 different live performances. Thank you. And sorry for the long...